Welcome back to the deep dive. Today, we're embarking on an exploration of a concept that's really foundational in engineering. It often sounds, way more intimidating than it maybe is. The moment of inertia, our mission, to kind of distill the core insights from our source material, demystify this pretty critical idea, and give you a shortcut to truly understanding why it matters. I mean, think about it. When engineers design something common, like a structural beam, why is calculating its cross-sectional moment of inertia so important? It's really all about predicting how it'll behave under stress. How strong it's going to be, how it resists bending.
Yeah, and what's truly fascinating here is just how pervasive moments of inertia are. The name might sound really technical, like straight out of a physics textbook, which, okay, it kind of is. But this concept, it really underpins everything. Fluid dynamics, mechanics and materials, structural mechanics, even mechanical design. Our main source for this deep dive is a pretty solid textbook chapter, and it really lays out just how fundamental this property is across loads of engineering fields.
Okay, so let's break it down then. What exactly is a moment of inertia for an area? The material defines it formally using integrals. It's like the sum of tiny areas, each multiplied by the square of its distance from an axis. You often see it written as ADA or X study A, and it's sometimes called the second moment of the area, right? Because that distance is squared.
Exactly. That square distance is the key thing. And it's interesting, it has this parallel to the mass moment of inertia, which is more about dynamics, how things resist spinning or angular acceleration. The math looks really similar. The AADA versus AADM. One's about how areas spread out. The other is about how mass is spread out.
Okay, so it's like a geometric measurement.
Precisely.
Mm-hmm.
And if we connect this to the bigger picture, it's crucial to get that for an area, the second moment doesn't really have a direct physical meaning on its own. You can't hold it in your hand.
Mm-hmm.
Instead, it's a critical geometric property. Think of it like a number that tells you how effectively an area's shape is distributed away from an axis. The further the material spread out, the bigger the moment of inertia.
And engineers use that number to figure out strength.
Yeah, exactly. It's used to determine the strength of a structural member or how much it'll resist bending. Or another example from the source. Think about a plate submerged in fluid, like water pushing on a dam gate. The pressure increases with depth, pk. They are total turning force. The moment from that pressure is m equals yda, that integral. That's our moment of inertia.
Ah, okay. So it pops up in fluid mechanics, too.
It does. And some key properties to remember. Moments of inertia, x, a, and also the polar moment of inertia, jo. It's basically ax plus aa. They'll always be positive values, because you're squaring that distance term, right?
Yeah.
And the units are always length to the fourth power, so meters to the fourth or inches to the fourth, something like that.
Right. Length times length times length times length times length. Got it.
Yeah.
Now, here's where it gets really powerful. Maybe the first big aha moment for engineers. The Parallel Axis Theorem. This sounds like a massive shortcut.
Oh, it absolutely is. It's a total game changer. What it lets you do is find the moment of inertia of an area about any axis, as long as it's parallel to an axis that goes through the area's centroid, its geometric center. And you have to know the moment of inertia about that centroidal axis first.
So if you know the value for the center axis, you can easily find it for any other parallel axis.
Yep, the formula is pretty straightforward. Rx plus 80 plus, Here, Rx is the moment of inertia about the centroidal axis, A is the total area, and aread is the perpendicular distance you've moved the axis. There are similar formulas for the Rx and the polar moment, Jo.
And why is that Rx term, the centroidal one, special?
Well, mathematically, if your axis goes right through the centroid, a related term, the integral irrigate, actually becomes zero. That simplifies things. But the theorem itself elegantly says the moment of inertia about your new axis equals the centroidal one plus this extra bit area.
That error term seems important.
It is. It clearly shows that the further you shift the axis, increasing d, or the larger the area A, the more the moment of inertia increases. And more importantly, it shows how distributing the area further away from the centroidal axis dramatically increases the moment of inertia about that centroidal axis. Think about an I-beam again. Why that shape?
Because most of the metal is in the top and bottom flanges, far from the center.
Exactly. That maximizes the distance squared effect for those areas, making it really strong and stiff for bending using less material than a solid square beam would need. That adjunct term is working hard in an I-beam.
Okay, that makes sense. Our material also mentions something called the radius of gyration.
Ah, yes. That's a quantity often used, especially when designing columns to resist buckling. The formulas are like KRX XA. It basically turns the moment of inertia back into a kind of representative length.
So it's not a physical radius.
Not exactly, no. It's more like an effective radius,
Yeah.
representing how efficiently the area is distributed to resist bending or buckling. Imagine you could concentrate all the area A into a thin strip at a distance k from the axis. That strip would have the same moment of inertia Ix as the original shape, because IRE is Alkite 8. So a larger radius of gyration means the shape is better at resisting buckling, generally speaking.
Gotcha. In calculating these, the source mentions choosing different ways to slice up the area for integration.
Right. When you do the direct integration, AYOP, you have choices for that little area element, dA. You can use a thin strip parallel to the axis you're interested in or perpendicular to it. Often one choice makes the integral much easier to solve than the other. Experience helps pick the simpler path. Example 10.3 in the source likely shows this.
Okay, so theorems and clever calculation tricks help. But real-world parts aren't always simple rectangles or circles. What about complex shapes?
Good question. That leads us to composite areas.
Hmm.
Most real structural shapes are complex, right? Like a T-beam or an angle section or a plate with holes cut out. The idea is you break that complex shape down into a collection of simpler parts, rectangles, triangles, circles, things you already know about.
Like building blocks.
Exactly like building blocks.
Yeah.
And the key principle is the moment of inertia of the whole composite shape is just the algebraic sum of the moments of inertia of all its simpler parts. But, and this is crucial, you have to calculate the moment of inertia of each part about the same reference axis for the whole shape.
Ah, so you can't just add up their individual centroidal moments of inertia.
No, you can't. That's where the parallel axis theorem becomes absolutely essential again. You follow a procedure. First, mentally divide the complex shape into simple parts. Find the centroid of each part. Then, for each simple part, use the parallel axis theorem, I plus additor, to find its moment of inertia about the common reference axis you've chosen for the entire composite shape. That d is the distance from the part's centroid to the common reference axis.
And then you just add all those calculated I values together.
You add them up. And if one of your parts is actually a hole or a cutout,
You subtract its moment of inertia?
you got it. Treat its area as negative, basically,
Yeah.
and subtract its contribution, calculated using the parallel axis theorem relative to the common axis. The examples in the text, like a rectangle with a circular hole or that T-beam, show this perfectly. It lets engineers analyze almost any cross-section you can imagine.
Okay, that composite method seems really practical. Now let's shift gears a bit. The source introduces another concept, the product of inertia. This one sounds less intuitive.
It can be, yeah, XE-XEDA. Unlike XEI, which involve Y or XI, this involves the product DAXI. Its main purpose, as the source states, is that it's needed to figure out the maximum and minimum moments of inertia for an area when the axes are rotated.
Why do we need the max and min values?
Because those represent the axes where the shape is strongest and weakest in bending, you could say, or most and least resistant. Knowing these principal moments of inertia and the orientation of those axes is super important for designing beams, columns, shafts, anything that might experience complex loading.
And this ICSI value, it can be negative.
It can. That's a big difference from X and I. The product of inertia can be positive, negative, or zero. And here's a key insight. If either the x-axis or the y-axis is an axis of symmetry for the area, then the product of inertia ICSI is automatically zero.
Symmetry makes it zero. Why?
Think about it. For every little area element x and a at coordinates, xy, if there's symmetry, there's a matching element at xy or x and au. When you multiply x times y, those contributions cancel out in the sum base dA.
Right.
So a non-zero XE tells you about the asymmetry of the shape relative to your chosen x and y axis. Like an L-shaped bracket, it's definitely not symmetric about standard axes through its corner.
Okay. And does the parallel axis theorem work for this too?
It does. There's a version for the product of inertia. XEX equals XEX plus A dx. XEX is the product of inertia relative to the centroidal axis, A is the area, and dx and di are the distances you shift the origin from the centroid to your new reference point. Super important here. You must keep the algebraic signs for dx and di. Whether you move left, right, or up, down matters.
Got it. Signs matter for dx, di. So this helps calculate ICSI for composite shapes too.
Yes, using the same logic as before. Calculate x's for each simple part, which is often zero if the part is symmetric about its own centroidal axis, then use the parallel axis theorem to shift it to the common axis, keeping track of dx and ic signs, and sum them up.
And this leads to finding those principal moments by rotating the axis.
Exactly. Sometimes the standard xy axes aren't aligned with how the structure naturally wants to bend. So engineers need to calculate the moments and product of inertia, EQ, IV, EQV, relative to a set of inclined axes, say U and V, rotated by some angle from x and y. There are transformation equations given in the source that let you calculate IQ, ACG, and IGI if you know XI, XC, and angle x.
Okay, so some trigonometry involved there.
There is. But the goal is usually to find the specific angle where the product of inertia IU becomes zero. Those axes where the product of inertia is zero are called the principal axes, and the moments of inertia about those axes are the principal moments of inertia, the absolute maximum, Imax, and minimum, Emin, values for the area.
And any symmetrical axis is automatically a principal axis.
That's right, because we know the product of inertia is zero if an axis is one of symmetry. So symmetry gives you a head start on finding the principal axis.
Okay, those transformation equations sound potentially complex. Is there an easier way to visualize or calculate these principal values and the angle?
Yes, thankfully. This is where Moore's circle comes in. It's a really clever graphical method. Equations 10 to 9 to 10, 11 in the source, the transformation equations, can be represented visually by this circle. It's often easier to use and remember than plugging into formulas.
How does it work, basically?
You set up a graph. The horizontal axis is for the moment of inertia, and the vertical axis is for the product of inertia. You plot a specific point representing the state on your initial x, y-axis its coordinates are ix, xc. Let's call this point A. You also know iy. Then you find the center of the circle, which always lies on the horizontal y-axis, the average value, is plus iy. With the center C and the point A, you can draw the circle.
And where are the principal moments on this circle?
The circle intersects the horizontal y-axis at 2 points. Remember, the horizontal axis represents where the product of inertia is zero. Those two intersection points give you your Imax and Imin, the principal moments of inertia. Directly read off the graph.
Wow, okay, and the angle?
The angle on the circle, measured from the line connecting the center C to your reference point A over to the horizontal axis, is related to the angle you need to rotate your actual axis, xy to u, AV, to get to the principal axis. There's a factor of 2 involved. An angle 2 on the circle corresponds to an angle in reality, but it's straightforward to find the orientation.
So Moore's circle is like a graphical calculator for axis rotation problems.
Pretty much. It neatly visualizes how I and axis change as you rotate the axes and quickly identifies those critical maximum and minimum values and their orientation. Very useful tool.
All right, that covers area moments quite thoroughly. Now let's shift focus, like you mentioned earlier, to the mass moment of inertia. How is this different?
The core difference is in the application and what it measures. Area moment of inertia, as we've discussed, is a geometric property used mainly in statics and mechanics of materials to determine stress and deflection, resistance to bending. Mass moment of inertia, I, is a dynamical property. It measures a physical body's resistance to angular acceleration. How hard is it to get it spinning or to change its rotation speed?
So this is for things that are actually moving, rotating.
Exactly. It's fundamental in dynamics when you're studying rotational motion. Think flywheels, gears, planets, anything that spins is defined similarly but with mass. I store your dm. Here, dm is a tiny element of mass, and r is its perpendicular distance from the axis of rotation.
And the units reflect the mass component.
They do. Kilogram meter squared, kgm in SI units, or slug foot squared, slag 2 hem in US customary units. It clearly involves mass. If the body has a constant density, you can write dm as Br dv, density times the small volume element, so I.e. in Br dv. You integrate over the volume.
How do engineers typically calculate this for real objects?
For objects with symmetry, the source mentions using shell or disk elements for integration. A thin cylindrical shell element is useful if all its mass is roughly at the same distance r from the axis. A thin disk element is better if the object extends radially, like integrating slices of a cone or sphere. You often find the disk's moment of inertia first, then integrate those disks.
Now let me guess. The parallel axis theorem applies here too.
You bet. It's just as powerful for mass as it is for area. The formula is IE plus mdr. Ig is the mass moment of inertia about an axis passing through the body's center of mass. Gm is the total mass of the body. And d is the perpendicular distance between the axis through G and the parallel axis you're interested in.
So again, if you know the value through the center of mass, you can find it for any parallel axis.
Precisely. And this is key for composite bodies. Objects made of several simpler shapes joined together, like a pendulum made of a rod and a disc. You find Ig for each simple part, rod, disc. Use the parallel axis theorem to shift each part's moment of inertia to the common axis of rotation for the whole assembly, and then just add them up or subtract if removing mass.
Is there a mass version of the radius of gyration too?
Yes, the mass radius of gyration, k, defined as k erie, or rearranging, IEEA in Shea Physia. Again, it's a length that represents how far from the axis On average, the mass is distributed in terms of rotational inertia. It tells you if the mass is concentrated near the axis or spread far out.
Useful shorthand sometimes? Wow. We've really covered a lot of ground today. We've gone on quite the deep dive, uncovering these fundamental concepts of moments of inertia, both for areas and for masses. We looked at the basic definitions, these second moments, saw how the parallel axis theorem is such a crucial shortcut. We got into the product of inertia, how it relates to asymmetry and helps find principal axes, and even that cool graphical tool, Moore's circle. And then shifted to mass moment of inertia for rotation. It really seems like from predicting beam strength to understanding flywheel motion, these concepts are, well, they're everywhere in engineering.
They really are foundational. And maybe this raises an important question for you, the listener, to consider. Now that you have a better feel for these second moments, how distributing material affects resistance, why symmetry matters, what principal axes signify, even how it applies to spinning objects, how might that change the way you look at everyday things? Think about, I don't know, the design of a bicycle wheel versus a solid disc, or why some tools feel balanced and others don't, or even how a cat manages to twist in midair. These principles of distributing area and mass are quietly at work all around us.
That's a great point, a fantastic thought to end on. Hopefully this deep dive has given you a new lens, maybe, to view the hidden mechanics and the often quite clever design behind the structures and machines that shape our world.